Okay, so a very good afternoon, everyone. I'm Vijay Tan, and as a final presentation, I would like to present my project that entitled "The Development of an Efficient and Seamless Multidisciplinary Design Optimization Process for Airframe Design." Before I begin, as there are some construction work around my apartment, so if there's any noise, sorry about that, and I hope everything will just go well. So as ESR 5, the main focus of my project is to improve the overall integration among the software in Airframe MDO. MDO is a multidisciplinary design optimization, in case there's anyone that's not too sure about it. So I will begin with my project overview. So in general, airframe design can be split into three phases, which are the conceptual, preliminary design, and detailed design phases. So MDO platform is a powerful tool that has gained traction in the recent decade, and it has been successfully applied in various stages of aircraft design. Currently, for airframe MDO specifically, not aircraft MDO, is mainly available from the later stage of conceptual design to the preliminary design stage. Therefore, the goal of my project is to expand the capability of airframe MDO in both directions. First, to early conceptual design phase, and second, to detailed design phase. So for this project, there are three design tools that are involved. First is Descartes, which is a model generator in conceptual aircraft design. Next is Lagrange, which you already experienced from my colleagues. It's a multidisciplinary design optimization platform. And last but not least, we have Strength 2000, or in short S2K, which is a software to assist the process of airframe certification. So as you can see, the project can be split into two parts, which are first, the integration between Descartes and Lagrange, and second, the integration between Lagrange and Strength 2000. I'm now finishing up the work in part 1 and starting a bit with the work on part 2. And ultimately, once the whole integration is completed, we'll be able to obtain a size and certified design from a conceptual airframe design. So for part 1 is about the integration between Descartes and Lagrange. This flowchart is a simplified representation in order to perform a sizing optimization from a CPACS model to with the Lagrange optimization. So CPACS is a parametric design language or schema. In other words, it's a XML schema that has been developed by the German Aerospace Center. So in CPACS, there are quite a lot of components which you can define, like wings, ribs, spars, and so on. Those are the common aircraft parameters. So as you can see, the green ticks here are more or less the connection that has been integrated prior to my work. As you can see, Descartes is a tool that can consume a CPACS model and generate an arrow model and a finite element model. And without a doubt, it's also possible to extract design variable and constraint, as well as flight and mass configuration easily from XML data. So these are the green ticks here. And for my project, for my work in part 1, are the missing connections over here on the right hand side of the work. So first, the how should I put it? So the first item that I like to point out is the finite element model. Even though Descartes can generate a finite element model as such, there are still a missing component which we call it the structural interface. In short, we are referring to the connection between the large components such as the wing and fuselage. So as you can see over here, there are two main types of structural interface. One of them is like this, and the other one is the bottom one. So I have separate them into two. This one will be the point joint, as there are just a few points of connection, whereas the other one, I call it a continuous joint, because the connection, although it's not really a continuous, but it's as good as a continuous welded joint. So and the continuous joint is a joint that you can typically found in the commercial passenger aircraft. And for these two joint types, if you would like to have a finite element model, okay, that was a slight mistake. Okay. So it's not really visible over here, but the finite element model generated from at the beginning of the from Descartes was there are no appropriate element for structure interface, and the first part of my project is to implement these items. So continuous joint already has designated elements in the CPAC schema, but there's none for point joint. So therefore, I have defined the schema for the point joint, and on the left hand side over here is the illustration of the finite element models of the point joint. I'll not go into detail, but it's pretty similar to the connections of the what is it called, of the control surface track. So next, I would like to talk about the other aspect of the integration between Descartes and Lagrange. First of all, there's still another intermediate tool, which is called DevOps, that helps to split structures such as a wing shell into smaller patches, such that they can have be assigned design variables and buckling constraint to them. Besides that, therefore also help to define the symmetry ply constraint for a composite shell. Moreover, from CPACs directly, I have also defined strength and gauge constraints as the initial implementation, and in the future, I will possibly include more other constraint that is available in Lagrange as required. There's up to a discussion later on. And up next is the coupling between aerodynamic and structural models. This is for the coupling between aerodynamic and structural model is just the nodes to transfer the load of the aerodynamic forces to the structural model. And besides that, we also have flight condition in trim state. Trim state in this case is referred to the steady state during several flight cases, such as a takeoff, cruise, pull out, and push over. These are the 4 typical cases that will be automatically available when you even though it is not defined in the CPAC schema. So this is given as a gift in a way. And then for flight conditions, we also need to define the several design variables, which are the angle of attack of the aircraft and also the control surfaces. And in Lagrange, it will perform a optimization to calculate what is the right angle of attack and control angle of attack for the aircraft and the control surface, such that the flight will generate the sufficient lift to maintain the one of the steady states here. And lastly, we also have the mass configuration, which is referring to the distribution of the cargo, passenger, and fuel in the aircraft. This has to be defined by the user in the CPAC schemas as is important, such that the aircraft can be balanced in the Lagrange optimization. So for part 2 of the project is the integration between Lagrange and Strength 2000. So Strength 2000 is initially developed by Airbus to simplify the task of creating reports for certification or validation process. This has not only used in detailed design phases, but also in maintenance work as well. So in Strength 2000, there are couples more validation and certification checks than in the Lagrange MDO. So the idea is to have integrate these checks from Strength 2000 such that the optimized model from Lagrange will also be able to pass the certification check directly, so that we can save time and effort to change the design later on. So for this integration, the aim here is to create an interchange format to facilitate the communication between them. Besides that, creation of an interchange format will also enable plug and play with other certification tools as well. So once both of this integration is completed, we will be able to have a fully integrated airframe optimization with certification, such that we can vary the CPACs, we can vary the airframe design, such as changing the frames, spars and ribs and placing and so on, and directly we can obtain a size, a correctly sized and certified design in one steps, which was not previously we were able to do so. So at the moment, the designer can usually perform, let's say, 2 to 3 different airframe and perform 2 to 3 airframe layout analysis, and then we'll have to decide on the exact. We'll have to make our mind on one of the design and proceed into the preliminary design cases, at preliminary design stage. So all this integration will enable more design freedoms during the conceptual design phase. So that's all from my presentation. And before I end this presentation, I'd like to thank you, all these people, for their support throughout my project. Thank you.
Many thanks, Wei Chai, for your presentation.